Today we're going to talk about stereochemistry because we talked about alkanes. And alkanes are single bonded. So maybe I take a butane like this. And remember that there's hydrogens posted on the ends of these methyls here, right? Because every carbon has 4 actual bonds. So if I draw a butane like this, and I see that carbon here only has 2 bonds, one to each of its neighboring carbons, there must be a couple hydrogens hanging off here. Maybe a couple hanging off over here like this, and then 3 hydrogens this way. We talked about how alkanes are always going to be like a C3H8, which is the number of carbons times 2, and then you add 2, and that's how you get to 8 hydrogens. That's the most saturated an alkane can get. And that's really important to remember because as we look into cycloalkanes and some other things, there's going to be other options for us. Well, let's take this away too, because I want to use something really simple while we talk about stereochemistry. I'm going to talk about ethane. Okay, so here's a carbon and here's a carbon. And these are each attached to 3 hydrogens like this. And of course, we're learning how to draw molecules without these, but for now, I'm going to put these in for today because I want you to think about this in a 3-dimensional way. Remember, this isn't a 2-dimensional universe that we live in. And this sigma bond here, this single bond between these 2 carbons, let's take these hydrogens away again. I'll bring them back in a second here. But this single bond between these carbons, it's allowed to rotate in this way, like an axle on a car. If you're single bonded, there's nothing to stop these 3 hydrogens from rotating like a wheel as they're attached to carbon. And same with the 3 over here, they could be going the other direction. Doesn't really matter how you depict it. So if I'm to look at it, and I want to draw these hydrogens in here like this, on each side, well, if I'm looking right down the pipe from this way, right through this, like so, I'm going to see something like this. Of course, the hydrogens will be as far apart as possible. My carbon will be in the middle here. And then in the background, if it was in 3D or something, you're looking from above, you would see, you wouldn't even be able to see this guy here because it's exactly lined up right here as I'm looking from this direction. But what's cool about it is that we know in stereochemistry that would put these hydrogens close together if they're lined up perfectly. And so that's not really what happens. This group here is going to want to be at an off angle. I'll do a dotted line for these guys here. How can I do that? Let's take these bonds out here maybe, like this. That's good enough for what we're doing. And I'll make it a dotted line, just so you can see which hydrogens I'm talking about here. That's these guys here. So they're farther back, they're farther away. And you'll see something like this. So if I'm looking at it maybe at kind of a perspective angle, then you would see, again, I'll do a dotted line here, like this. Because that makes these hydrogens as far apart as possible. This one has kind of a distance to get to this hydrogen out here. Rather than have them lined up perfectly like these appear to be here, that's too close. So this configuration right here is going to be the lowest energy. We'll call it low energy. And we call it a conformation. And that just means the way that the molecule is arranged. That's a conformation. So because these are symmetrical in their sigma bond, meaning like they have the same thing on each side, then there's going to be an energy balance established here somehow. And if you like draw this in perspective this way, I think they call this a sawhorse projection. If you look at it dead on like this, they call that a Newman projection. This is called Newman projection, not because it's low energy, but because you're looking at it down the pipe, where you can only see the front carbon here, this guy. You can't see this guy behind him. You're looking right down that axle there. So When this is arranged in low energy, this is called a staggered conformation. Conformation being the arrangement, staggered meaning that the hydrogen, 3 hydrogen complex on each end of this methyl, like one methyl here and one methyl group here, they're offset by the maximum angle possible to make the distance between these hydrogens as far as possible. And that's what they really want. So if I'm like having fun with this, you'll find that if I want to rotate this, like say I take one end and I decide to rotate it, the energy goes up and then back down every time I rotate a hydrogen past the other one like that. So this low energy space here is where you would have, I'll draw the projected version here, this kind of thing here where it doesn't really line up with anything else. But over here at the high one, that's where ethane is arranged like this. And these are closer here than these are here, thanks to the rotation. So if I'm at a higher energy point for ethane, you're going to see that by the conformation itself. I think they call it an eclipsed conformation here because they're lined up perfectly, which is why I wouldn't be able to see it if I was looking down the pipe here. You would only see just the front one. That's really important to keep in mind, and it's really not too complicated. It's just important to remember that with sigma bonds, because these can always rotate freely, that if I'm going to add energy to the system, then they may line up this way, meaning the hydrogens line up along their 2 methyl groups that might line up this way. But a staggered conformation here is my low energy version. So if I'm cooling it down, definitely the molecule is going to form this version here. If I'm heating it up, maybe you see some of this action over here. And that's all we need to know for conformations and Newman projections for now. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.